Welcome everyone. In today's lecture, we will discuss about the importance of quantum mechanics in photovoltaics. In last two lecture, we have discussed about different source of energy. For example, we have talked about conventional source of energies like coal, natural gas and oil, and we have also discussed about non-conventional source of energy like wind energy, tidal energy, geothermal energy and solar energy. We also said that based on their resources, this kind of energy can be classified into renewable and non-renewable energy. And finally, we discussed about the solar energy, and we said that out of the different forms of renewable energy, solar energy is a clean and green source of energy, and it is very popular. Now, in this course, we are going to study about the solar cells in details. To understand the solar cell, it is very important to have a preliminary and basic concept of the quantum mechanics. In this course, we are not going to learn in details about the quantum mechanics, but we will learn that much amount of quantum mechanics which is needed to understand the working principle of a solar cell. So, for getting a complete insight of the photovoltaic solar cell, it is important to understand the basic concept of quantum physics. The behavior of matter and energy is different at subatomic scale than the macro scale. So, quantum theory is usually essential to understand the behavior at the subatomic scale. And the principle of quantum mechanics that can be applied for developing better PV cells with higher efficiencies and molecules. So, what do we mean by that? Let us give an example. Okay, let us consider this chalk. This is a bulk material. Now, if I throw this chalk with some kind of force, let us say 10 Newton. So, we know that this chalk will go and then it will hit some positions. If I know its initial velocity, and since we know its final velocity is 0, so we can calculate how much distance it will move. Okay? Or if we know its final velocity, if we know its distance, then we can find out its initial velocity. If I make this chalk half, let us say I cut it into two pieces, and if I throw each of this piece with 10 Newton force, I can again calculate by using the Newton's law. But let us imagine a situation I keep on doing this, cutting this chalk, and comes to a dimension which is something like 10 to the power minus 9 meter, or which is like 10 to the power minus 10 meter. In that scale, when the chalk is there, we call it, for example, nano chalk. The question is whether we can apply the similar amount of 10 Newton force to this nano chalk, or even if we apply, whether we will be able to calculate the distance it will cover. So, this is a big question. The question is not about whether Newton's law is right or wrong at the subatomic scale, but the question is, it is the scale which prohibits the use of the Newton's law at such a small scale. When we talk about electron or proton or neutron or any other subatomic particle, we cannot directly use Newton's law of motions. To find out the kinematics of any particle or any subatomic particle, we simply cannot directly use Newton's law. It does not mean that Newton's law is wrong, but it is the smallness of the scale which prohibits us to use this Newton's law in that scale. So, how we describe the kinematics or motion of this particle? We all know that flow of the electron is the current, and in a photovoltaic solar cells, we basically are going to study about this current and voltage. Now, this current is coming due to the flow of electron. Now, to understand this flow of electron, we really need to understand what kind of force is acting on them, and if a certain kind of force is working on them, what will be their trajectory, what will be their motion. We cannot explain this in terms of the classical physics or classical mechanics. A completely new kind of mechanics or completely a new kind of physics is necessary to explain this, and that is what the quantum mechanics. And the quantum mechanics evolution has happened over quite a long amount of time. J.J. Thomson first gave the concept of the electron. Later on, Rutherford, from his famous alpha particle scattering experiment, has said that most of the space in the atom is free and there is a massive positively charged nucleus at the center of the atom, and electrons which are negatively charged particle, they orbit around the nucleus. Now, from the classical Maxwell theory of the electromagnetism, which was there in the place for quite a long time. So, this Maxwell's theory of electromagnetism, they say that any radiating or any accelerating electric charge, they radiate. Now, if the electron moves in a circular orbit, let us say like this is the electron and it moves in this circular orbit. So, at each and every moment its direction is going to be changed. So, that means it is accelerating. So, if the electron accelerates like this way, very soon it will lose its energy and falls on the nucleus. For example, if we consider this is the atomic structure, I have my nucleus which is at the center, this is the nucleus, and electron is rotating around this nucleus. So, according to the Maxwell's theory of electromagnetism, very soon electrons will make a serpentine path and will fall on the nucleus. So, there will be no atomic stability, but in the contrast we all know that atoms are stable and all the solid exist. The second part from this Rutherford experiment, which was not able to explain in the classical physics, is the origin of line spectrum in the electromagnetic spectrum. According to the Rutherford theory, we should get a band like spectrum, whereas the spectroscopic has seen a line spectrum in most of the materials. Both of these anomalies were not able to explain by the Rutherford's theory, and it was understood that a completely new kind of theory is required to explain this phenomena. By that time, Einstein explained his photoelectric effect. So, what he says that extending the Planck's black body radiation, that when any hot body emits radiation, it not only emits the energy as a bundle of energy, but it also absorbs the energy in bundle of energy. So, that means if it emits the energy in bundle of energy and if it absorbs the energy in bundle of energy, when the energy is in the space, there also it exists as a bundle of energy. So, this bundle of energy he gave a name called photon. So, the quantum of this energy he gave a name called photon, and he described the light as a photon or as a particle. Phenomena like photoelectric effect, like Crompton effect, can be explained by this photon picture or particle picture of the light wave. At the same time, Niels Bohr came and he was trying to improve upon the existing Rutherford's theory. Combining the concept of the Einstein and the black body radiation theory of the Planck, Bohr has extended the idea of the Rutherford's Planck's model, and what he said that electron cannot move arbitrarily in any of the orbits like this, but it can rotate only in those orbits where its energy is fixed. So, if I fix its energy, so then electron in a particular orbital has a fixed quantum of energy, and this explains most of the dilemma or most of the anomaly existing in that times, and that was the origin of quantum theory. Now, so far we have considered the light either as a wave or as a particle. For example, when we want to explain phenomena like polarization or diffraction or scattering, we consider the light as an wave. We take an example for interference or diffraction, we consider light as a wave. But when we talk about photoelectric effect, we talk about Crompton effect, we consider light as a particle. So, that means light can exist as a wave and it can also exist as a particle. So, it has a dual nature. Now, we are already discussing about the electron's motion in the atom by then. So, the normal question which arises in the people's mind, if the light can exist as a wave as well as a particle, can particle also exist as a wave? And that's what comes the famous de Broglie's equations. De Broglie in his PhD thesis first proposed that any particle like electron can also exist like a wave, and he explained that things if this is an atomic orbital and if this is an electron, so this atomic particle electron, they can exist like a wave. And how does this wave will be distributed here? So this will be distributed like this. So here is the one very interesting point. When we talk about the electron as a particle, we talk about its charge, we talk about its mass. And if we know what is its charge and what is its mass, and if we know the centrifugal force, we can find out the location. But the moment we go to describe the electron as a wave, then we have distributed it over a dimension rather than restricting it at particular positions. Now if I ask you the questions at time t is equal to 10 second, where is this electron? So the probability of electron being here and here are same. You can say that electron is here, somebody can say the electron is here. So the point is that we cannot definitely say that electron is either here or here. What makes more sense, instead of telling electron is here or here, the probability of getting electron between this point and between that point is maximum, or probability of electron between this point and that point is maximum. If this point is represented by time t and if this point is represented by time t plus dt, so in a time interval between t to t plus dt, the probability of finding the electron between this point and this point is maximum. So now we are talking about in terms of probability. So quantum mechanics talks in the language of the statistical mechanics. Here we talk everything in terms of the probability. And when we represent the electron as a wave, so obviously there will be a wavelength associated with this electron, and de Broglie called that wavelength as a lambda, because if there is a wave, there will be a wavelength. But this is the wave properties of the electron. Now electron has a mass m, it has a velocity v, so that means it has a momentum which is m times v. This momentum is the particle properties of the electron, whereas this wavelength is the wave-like properties of the electron. How one can correlate this wave-like properties with this particle-like properties? That is what de Broglie did. So what he said that the wavelength of the electron lambda is equal to the Planck's constant h divided by the momentum p, and this wavelength we call as de Broglie wavelength, and h here is the Planck constant. Corresponding to every subatomic particle, whether it is an electron, whether it is a proton or whether it is a neutron, we can find out the corresponding de Broglie wavelength if we know the charge and mass of that particle. So what we are telling here, the electron which is a particle can also exist as a wave, and this kind of wave is called matter wave. In quantum mechanics, the state of any particle is represented by a wave function, and a wave function is usually written by the symbol called psi. Now psi is a quantity which represents the probability of finding the particle somewhere in this space. Another important point here is that in classical Newtonian mechanics, we mainly deal with the Euclidean geometry, but in quantum mechanics we consider the complex space. In quantum mechanics, the probability density makes more logical sense than the only wave function. So since psi is a complex quantity, I can find the positive quantity, that the position probability density, by multiplying the psi with its complex conjugate. Let us take an example. Let us take an arbitrary complex number a plus ib. What will be the complex conjugate of this quantity? A minus ib. If I multiply z with z star, I will get mod of z square, and that is equal to A plus IB times A minus IB. You get A square plus B square. And this is the really useful physically measurable quantity. Similarly, if your wave function is psi, if I multiply it with complex conjugate, which is called psi star, then you get mod psi square, which is called position probability density. And this position probability density is physically more significant than the wave function. And wave function is always a function of the positions and times. So, these are the some fundamental postulates of quantum mechanics which is important to learn in the beginning before we go to the kinematics equation which govern the quantum mechanics. So, in quantum mechanics, the state of a particle is represented by the wave function psi, and the probability of any particle or finding of any particle is represented by the probability density, and probability density is physically more meaningful than the only probability. Okay, let us come back to our photovoltaic systems. Most of the time the solar spectrum comes like this spectrum or rainbow. Now, on the left hand side I have red photon. Red photon is larger wavelength photon, that means they have low energy. And the right hand side we have blue photon, and blue photon is have a lower wavelength, that means they have higher energy. For time being, consider this is my solar cell and photon beams falls on these solar cells. So, what will happen? There will be an electron which will absorb this photon beam and it will go from the ground state to the excited state, and the electrons will start moving from here and the whole will move in the opposite directions. If we connect a load in the outside circuit, we will get a current in the outside circuit. Now, if this energy is Eg, the band gap, which corresponds to Eg at the spectrum. Now, this part of the spectrum which is red photon, that does not contribute to the absorptions, so that get lost. Similarly, the blue photon, they have a slightly higher energy than the band gap energy. So, this part is the excess than the band gap energy. So, that excess energy will get lost by the heat energy to the crystal. So, the only useful energy is 30 to 35%, which we can harness from the spectrum. But our goal is to make a highly efficient solar cell, let us say for example 65% solar cell. How can we do that things? Either we need to use the whole spectrum, or we can do it by intelligently designing new materials or new interfacial layers on our electrodes so that the band gap can be tuned properly. To do this thing, we need to understand also the quantum mechanics very well. So, that is why a basic idea of quantum mechanics is very necessary. In classical physics, Newton's law describes the kinematics of a particle. If I apply a force F, if I know the mass of the particle m, so we can write from Newton's second law, force is equal to mass times accelerations. We can find out what is the accelerations. So, in classical mechanics, the position of a particle can be described as a function of force. But quantum mechanics, we just gave an example of a nano chalk. When you are talking about the electron, proton, how can we find out these positions? What equation govern the time evolutions of this wave function? So, that was given by Schrodinger equation. Schrodinger equation is actually a mathematical formulation for studying quantum mechanical system. It describes the change over time of a physical system in which quantum effects such as wave particle duality are significant. When we discussed about this de Broglie hypothesis, we said that the electron can also exist as a wave. So, that means electron can exist as a particle, it can also exist as a wave. So, it shows a dual nature, and that phenomena is called wave particle duality, and that is purely quantum in nature. Schrodinger, who formulated these equations, he discovered this in 1925 and published his work in 1926. And because of his outstanding work, he was given Nobel Prize in Physics in 1933. There are different formulations of quantum mechanics, like Schrodinger formulation. Similarly, there is a matrix formulations of the quantum mechanics, and also there are path integral formulations of quantum mechanics. Paul Dirac, he has combined the Schrodinger formulation and matrix formulations. Here we are not going in details about the all different formulations. We will learn about the Schrodinger equations and how we can use this Schrodinger equation to understand the dynamics of a system. The Schrodinger equation in one dimension is written like this: I, which is an imaginary number, times the reduced Planck's constant, which is called as h bar. If h is my Planck's constant, h by 2 pi, that is called the reduced Planck's constant h bar. I h bar, partial derivative of psi with respect to time is equal to minus h bar square by 2m, double partial derivative of psi with respect to position plus v psi. So, what we just written that I h bar del psi del t is equal to minus h bar square by 2m del 2 psi del x2 plus v psi. Here psi is my wave function, which is a function of position and time, and h bar is the reduced Planck's constant, and v the potential energy, v is the potential energy. Now, you look at this equation, the right hand side we have minus h bar square by 2m del 2 del x 2 psi plus v psi. So, we can also write the right hand side by minus h bar square by 2m double partial derivative with respect to x plus v, if we consider the v as an operator, times psi. In quantum mechanics, every physically measurable quantity is represented by an operator. Let us say I want to measure the length of this chalk. In classical mechanics or in classical physics, what I should do? I will take a normal scale, I will put the one end of the scale in one side, and then I will put the another side in here, and I will measure what is the length either in inch or in centimeter. But in quantum mechanics, we cannot measure the positions of this chalk like this way. We cannot use a scale there for the case of the electrons or protons. So, if I want to measure the positions of this nano chalk, let us consider this chalk is no longer a bulk chalk but a nano chalk, and I want to measure the length of this chalk, and let us say the length of this chalk is x, okay, this x. Now, this x in quantum mechanics is represented by putting a hat or cap sign on top of this x, and this is written as this is spelled as x hat or x cap, and this is called operator. Corresponding to every dynamical variables, there is an operator in quantum mechanics. Like momentum, they have an operator called momentum operator. Energy has an operator that is called energy operator. And when this operator operates on wave function, I get the result of measurement. The result of measurement in quantum mechanics is called expectation value. And another weird fact associated with quantum mechanics is that it says that every time we do a measurement, the system falls in a completely different system. So, next time when we do measurement, we are not measuring on the same system. Third time when we are doing measurement, we are not measuring on the same systems. So, every time we are not measuring at the same system. So, finally, after doing n successive measurement, what we get is an ensemble average of all successive measurements, and we call that measurements value as an expectation value. And the expectation value of this length x, that is represented by a symbol like this. And mathematically, this expectation value is calculated by putting the operator on the wave function, and to make it more physically meaningful, we learnt that to multiply it by complex conjugate and integrating over the space on which the electron is confined times the integrand. So, this bracketed part here, that corresponds to a operator in quantum mechanics, and this operator is called the Hamiltonian operator H. The first part here corresponds to the kinetic energy and the second part here corresponds to the potential energy. So, sometimes if you replace this whole part under this bracket by this letter H, so then this becomes H times psi. So, basically what we have written is that I H bar del psi del t is equal to H psi. That is the one dimensional Schrodinger equations. Now, this equation depend on the positions as well as the time. So, this is an example of a coupled equation. We need to decouple them for practical application. So, that means we need to make these equations in such a way, one part will contain the time part, another part will contain only the spatial part, and this is done by a method called method of separation of variables. We also mentioned it here. You can see that the potential energy is also a function of the positions and the time, and the method we are going to use to decouple this equation is this called method of separation of variables. So, in this method we write this wave function psi, which is a function of positions and time, as an independent product of two functions, where the first function depends only on positions and the second function depends only on time. Now, all of we are exposed to little bit of differential calculus and integral calculus. Assuming that fact, let us do a partial differentiation of this psi with respect to positions and with respect to time. Let us do the time part first. So, if I do a derivative of this wave function with respect to time, what I will get? I will get del psi del t is equal to phi x df dt, because now it is a not a partial integral, it is a full integral. If I substitute this in my Hamiltonian equation, if I substitute this in my Schrodinger equations, what I will get? So, that is the time part, and the second part of the equation was the spatial part. Now, I have to deal with the spatial part. So, if I differentiate the spatial part two times, then I will get, if I do it one time, I will get del psi del x is equal to d phi dx ft, and if I do it another time, I will get del 2 psi del x2 is equal to d2 phi dx2 ft. Let us substitute this, the spatial derivative part and this time derivative part in the original Schrodinger equations. So, what we will get here is the following. The first part was I h bar del psi del t is equal to minus h bar square by 2 m del 2 psi del x2 plus v psi, right. So, if we plug in from the previous derivative, what we will get, that I h bar phi df dt is equal to minus h bar square by 2 m del 2 psi del x2. We have done it last time, that is d2 phi dx2 ft. If we substitute this, so we will get d2 phi dx2 ft plus v is the potential energy into the wave function psi, which is a product of phi and f. Now, if we divide the both side by phi times f, you divide the left hand side and right hand side by phi times f. What you will get here on the left hand side? You will get I h bar 1 over f df dt, and right hand side what you will get? Minus h bar square over 2 m 1 over phi d2 phi dx2 plus v. That exactly we are showing here. Differentiating psi xt with respect to time and position, we get del psi del t, which is phi into df dt, and with differentiating with respect to x, we get del 2 psi del x2 is equal to f d2 phi dx2. Now, if we substitute this in the Schrodinger equation and subsequently divide by the phi into f, we get a equation which looks like that. Now, you look, there is an interesting fact. The left hand side here is a function of the time only, and the right hand side here is a function of positions only. This side is a function of time, this side is a function of the positions. So, I have an equation where f1 is a function of time is equal to f2 is a function of x. How that can be true simultaneously? If both of them is equal to a positive constant A, and let us consider that constant is the energy E. So, if we consider that constant is energy E, so I can equate the left hand side I h bar 1 over f df dt is equal to E, and if we integrate this equation I h bar 1 over f df dt is equal to E, what we will get? I h bar df by f is equal to E dt. If we multiply that, we can also write df by f 1 over I h bar E dt, if the I h bar comes on the right hand side, right. So, 1 over I is, we can multiply top and bottom by I. So, this is I and this will be I square, and I square is minus 1. So, that means we will get minus I by h bar E dt. So, if we integrate the previous equations, this df by f, also this right hand side. So, what we will get? We will get f is equal to f0 e to the power minus I e t by h bar. This is the solutions of the time dependent part of the Schrodinger equations. So, this is the solution for the time dependent part of the Schrodinger equation, f is equal to f0 e to the power minus I e t by h bar. We have left out with the special part, and what was our special part? Our special part was this, minus h bar square by 2m d2 phi dx2 plus v phi is equal to E phi, where v is the potential, and this is called time independent Schrodinger equation. As you can see, the d2 phi dx2, here phi is now a function of the positions only, as you have defined it earlier, and phi is also a positions, function of positions. So, everything here is a function of positions, no time here. So, that is why it is a time independent Schrodinger equation. So, starting with time dependent Schrodinger equation, we have now derived a time independent Schrodinger equations, and once we come across this point, rest of the quantum mechanics is solving this equation for different value of the potential. When you are talking about the electron in a metal or electron is a semiconductor, basically we are going to solve this equation subjected to the different boundary conditions. We first start with a typical example. Electron in a metal. This is sometimes represented as particle in a box problem or particle in an infinite potential well. Let us say single particle like gas molecule is confined in a one dimensional rectangular particle box. So, you consider here this is your x axis, this is your y axis, the particle is confined in a one dimensional rectangular potential box. So, the potential energy between these two ends is 0, and at these two boundary potential is infinite. The length of this box is L. This particle can move freely within the region between x0 to L. Inside the box the potential energy is 0, but at the wall it suddenly goes asymptotically and becomes infinite. So, if the mass of the particle is m and its total energy is E, then we can write the time independent Schrodinger equation d2 psi dx2 plus 2m by h bar square E minus v psi is equal to 0. So, this is exactly the representation of the potential here. You can draw the diagram here also. So, this is your x axis, this is your y axis, this is your potential, the length or the dimension of this potential box is L. So, Vx is equal to 0 here and V is equal to infinite at these two boundary. We need to solve the Schrodinger equation at this region and also at this region. Here the potential described by this function. So, I have written that d2 psi dx2 plus 2m by h bar square psi is equal to 0, and you consider this 2me by h bar square as a constant k square. If you replace this as a constant k square, the equation will be d2 psi dx2 plus k square psi is equal to 0, and the solutions of these equations will be a to the power ikx plus b e to the power minus ikx. If we apply the proper boundary conditions, what we will get that the energy value is n square pi square h bar square by 2ml square and the wave function is a sin n pi x by L. We will conclude this module with this, and in the next class we will see that how this application of the boundary condition is going to influence our wave function as well as the energy level. Thank you.